זה, והשאלות. לא יודע, אתה רוצה שאני אסמן לך? אתה על זה, מה שאתה רוצה.
כן, אתה יכול לסמן לי ככה אחרי 40 דקות.
בסדר.
הנה, דגן. מה קורה, דגן? בסדר, תגיד, אתה רצית לעלות לזום לדגן? כי אין פה, לא חיבור אותי לכם. הבנתי. טוב, סבבה. אז לא צריך להתחלק. אוקיי, סבבה. יאללה, ביי.
I might be the annoying lecturer telling you to go progress forward. Only if you want. Yeah, okay. We will start. People will probably join alongside. So we're very happy. I'm substituting for Guy and Aviv today. Guy is sick, and Aviv is not here today. So substitute. We're very happy to have Eshkol Eytan here with us today. Eshkol has done his bachelor's at the university and a direct track to PhD at the Weizmann Institute with Professor Ilan Morel. Eshkol is currently a serious postdoctoral fellow at Golden, Colorado, working on cloud aerosol radiated effects with Dr. Dan Feingold. We're very happy that you're here with us today and looking forward to your talk.
Thanks. Thank you, Asaf. Yeah, I'm also very happy to be here. This is where Nathan taught me all the stuff that I know about dynamics, and Karen taught me all the stuff that I knew in the beginning about radiation. So fun to be here again and present some of the work. So today I'm going to talk about, show some of the stuff that I started to play with and study during my PhD, mostly focusing on the ring vortices in Cumulus clouds, which is something that is I kind of continued into my postdoc as a side project. Let's see if this works. Yeah, okay. So generally is to talk about the mixing of Cumulus clouds using high resolution LES simulations. And this work has been in collaboration with my group where I did a PhD from Weizmann under Ilan Morel, with a lot of help from Yael Arieli, and with a very tight collaboration with Alexander Chaim and also Martin Udi, who is part of this group. Yeah. So the outline for the talk will be that I'll first give some introduction to convective clouds mixing and its role in climate prediction and in climate models. Then I'll talk about the methods we were using in order to try and understand clouds more in the process level understanding of the mixing of clouds, of Cumulus, shallow Cumulus clouds, and then see how can that be related to the parameterization and how these clouds are being treated in climate models. And I'll present the results, which is the undiluted core or the parts of the cloud, the different clouds mixing processes that occur in different scales, and to construct a kind of a general picture of the structure of a Cumulus cloud, and we'll end up with a discussion. So for start, why do we care about clouds and Cumulus clouds and mixing? And this is usually why, because this is the latest IPCC report, where we see the general, all kinds of leading feedbacks to the system. So we know we have a radiative forcing on the system. We increase aerosols, we decrease aerosols, most importantly we increase greenhouse gases, which cause a warming. And then the question is, what is the response of the system to that initial perturbation? And this is usually quantified as the as the climate feedbacks. You see here, this is the net feedbacks. And this is all the leading feedbacks that I already mentioned from a few different reports. So we have the latest in red, this is the latest IPCC report. We have the CIMIC models and the older generation and the new generation of the CIMIC models. And we can see that first of all, the most important feedback is the obvious one, is the planet feedback, which means that as the planet warms, the temperature rises, so it emits more radiation out to space. So that's a negative feedback. The planet acts to cool itself as it warms. But then we also have the water vapor and lapse rate feedbacks, which were usually in the beginning they were treated differently, but now we treat them as the same. And we have the surface albedo changes, like ice melting and stuff like that. This is only the last report of the IPCC is the first time that people try to quantify the biosphere interaction with the climate system, and we have this feedback report. And then we have the clouds. And here you can see that clouds drive what is usually referred to as the uncertainty of climate prediction, and this is why it is. Though uncertainty, I think, is not quite the word that should be used, because it only means what's the spread of our models. We don't have ground truth, it's not a measurement, it's not really giving us a taste of uncertainty or quantification of uncertainty, it just gives us a taste of how much our models don't agree on, and you can see that they really don't agree about how to treat clouds, because it can move from a positive feedback into negative feedback. So what are the processes that drive this uncertainty or disagreement between the models? And this has been studied a lot over most of the last decade. A lot of what is called perturbed parameter ensembles, where you run GCM, you take one GCM, you run it many times with ensembles, but you change the parameters of the parameterizations once at a time over a spectrum of values. This is very computationally heavy, but then you can see what parameterizations, which is the simplified, all the stuff that the model cannot solve, so actually it's been parameterized, it's been treated in a simplified way with parameters, and what parameters drive the largest spread in the climate prediction. And this is just to give you a taste that most of these studies usually point down eventually that it's the cloud parameters, of course, but also it's the mixing, how you parameterize the cloud and the convective clouds mixing. So yeah, you have all kinds of different papers. When everyone who is interested could just look it up, or I can also send you this list of papers. But eventually they show that mixing is the driver of the cloud's uncertainty, which drives most of the uncertainty, or a big portion of the uncertainty in climate prediction. And today, I mean, I'm not working with GCMs in the large scale, I'm working on cloud physics. But I would like to point out to why I think these parameterizations are giving us such a headache. And this is basically because if we think of these parameterization in the simplest way, and this is Arakawa and Schubert, this is one of the papers that, and one of the methods that most of the GCM's parameterizations today are based on. And this is where they thought of a cloud field as many different kinds of plumes.
50 years old?
Sorry?
A 50-year-old paper?
Yeah, I mean, you know, things have been changed a lot, but this is the basis of the mass flux and the eddy diffusivity models. These will combine together later on, but yeah, this is what set the basis for it. So basically what we think is that we have in a point of a large-scale model, we have agreed we can't really solve all the detailed processes of clouds, and so we need to assume how this cloud field behaves, and we usually assume as if we have a lot of plumes, so we are taking actually a model of a plume, like a plume of smoke, same physics, and we assume that there's a cloud base, there is air coming, entrainment of air, where air comes into the cloud from the cloud base, being entrained out of the cloud top, and you have some turbulent small-scale mixing across the column of the cloud. And then you have all kinds of different side distribution of clouds, and this is basically how we parameterize clouds, all based on this horizontally homogeneous and steady-state plume. Steady-state, I mean quasi-steady state, of course. But this is one of the simulations that I conducted during my PhD, and you will see it soon. This is a shallow cumulus clouds. So you can see the scale of, sorry, this is 0 to 8 in terms of meters. So this is a shallow cumulus clouds with a passive tracer that I put here in the simulations where you can actually follow the flow in a Eulerian way. And you can see that the cloud is really inhomogeneous and transient thermal. So it has a very rich structural internal structure that keeps changing all the time. And this is a lot of it is due to the mixing. So the internal structure of the clouds demands to be better understood and maybe represented in our simplified models of clouds. So this is a cloud, this is how we used to look at it, and then you can ask, what are the different processes, why is it so complex, what are the different processes that drive this kind of an entity? And first, of course, we have the aerosols and all the stuff coming from the boundary layer or from the surface, the aerosols, the water vapor, the trace gas inflow to the clouds from the cloud base, and eventually they being entrained from the top. Of course, we have also entrainment at other layers. If we have a weak inversion here, many times we see those entrainment layers. And if you have a look at such clouds as go off the airport. But then we have all kinds of others. So we have turbulence in all its scales. So we have the convection, which is the size of the clouds. That's the largest part of the scale of the flow of the eddies. And you have smaller eddies going all the way down to a few meters and even centimeters. And we have the interaction, that's the dynamic part of the clouds, but then we have coupling, the interaction between the dynamics of the flow and the microphysics, where we also have the droplets and chemical processes, and the microphysics is the process, the droplets, they evaporate and condensate, they collide and then split, and all that happens, and that releases also latent heating, which affects the dynamics, and affects, of course, rain, which affects the best way that microphysics can affect the dynamic is having these strong downdrafts of rain once the droplets are big enough. And of course, it also affects the radiation. So it's the cooling, the long wave cooling of the radiation at the cloud top, and the radiation that is going in between the clouds. And all of that together combined these very complex, multidisciplinary processes that occur inside the cloud. And it's all eventually tightly related to mixing in a turbulent flow in the cloud. So first we were thinking, okay, so maybe we can find an island of sanity for all these chaos. What is the places that we can go to? And of course the answer was the adiabatic processes, which is the simplest thing that I learned here in my first year in the bachelor's degree. That's the simplest way to describe the atmosphere. So of course people have done it much before us, turning to try and understand how can you define adiabaticity in clouds. And that makes sense because if we have an adiabatic core, so adiabatic regions will be places that don't exchange energy or matter with the surroundings. So that means that they don't mix with the environment outside of the cloud. There is no sedimentation of droplets because matter falls from a parcel. So if you have a parcel of air, it can move on, condensate, and just do its thing, but not really exchanging energy and matter with the surrounding. And if we have this adiabatic core, so that would be pretty easy to estimate how does the water change, the droplet size distribution, or the amount of liquid water changes on this vertical column. Sorry for that. And then that kind of gives us a kind of a boundary conditions on the cloud. So in the center of the cloud, we can understand what's going on. We also understand the environment, and then we can maybe try to understand how these communicate one with another. So the first questions that we asked was how well can we define and measure the dilution of the cloud? What is the extent and structure of the undiluted cloud core? And how do the cloud and its core interact with the environment? And for that we use high resolution simulations because it's very important for us to solve all the fine details. So the methodology of that, the way we chose to do it is by simulating these single clouds, so it's very theoretical, but it's also very easy to analyze. You don't have much of it. It's very kind of a toy model, but that's an LES model, so it solves the turbulence very good, and it's very high resolution. So we run the clouds in 10-meter resolution in all 3 dimensions, a half a second in time. This is very high. Usually, LES cloud fields have been simulated with 100 or 50-meter resolution, and that is considered high resolution for atmospheric modeling. So here we go even to higher resolution, and soon you'll understand also why we chose 10 and to go much.
But this is a single cloud.
Yeah, so we have a few simulations of these very single cloud, very theoretical way to look at the cloud for the beginning, just to gain some first intuition to how it works. Also, so this is very computational demanding, and this is another reason why we have why we do single clouds, because we also want to understand the interaction between the turbulent flow and the microphysics. So we need to have a decent microphysical model. I mean, the microphysical model is the model that represents all the microphysical processes. How do the droplets grow and interact with another end of the flow? So for that we use Alexander Klein's model, the Hebrew University. We also added some stuff to it. It's been a process to improve it. So now we have very detailed turbulent flow and very detailed microphysics. So that should give us a very good cloud. The only problem at the downflow is that it's just a few clouds because we could only afford a few simulation clouds. Another added value is that I added a passive tracer into the model, which just means that we have these particles that don't have any weight. They just go with the flow. It's not Lagrangian though, it's Eulerian, in an Eulerian way. But it's just another scalar that is being dispersed in space with the attraction and the diffusion, the turbulent diffusion. And that allows us to really good understand how does the cloud is being diluted in a theoretical way. So this is how the tracer look like in a few snapshots. This is how it begin. So one tracer I just distribute below the cloud base, which you can see here. And now everything that goes up after 30 minutes where the cloud is reached its mature stage, you can really see the parts where the tracer didn't change its concentration or its mixing ratio from below the cloud. And then you can really see where you have these regions that haven't been diluted yet, or the blue part is where the environment, where you have tracer equals 0. So this is where you don't have any remnants of the subcloud layer. Of course, this is the diffusion, so this is the contours, the red contours are the edges of the cloud, and you can see that once the cloud dissipates, it leaves these tracers behind it. And these tracers could be considered as aerosols, water vapor, trace gas, all the stuff that are coming from the surface. But this is a theoretical tracer. We can't really measure it in nature, so what do? How can we measure it? So we turn to a measurable metric that have been used a lot, different equations, different ways to estimate the adiabatic fraction. And then we can compare it to our original tracer and see which method is the best way what's the best way to measure the adiabatic fraction. And the adiabatic fraction is defined as the amount of liquid water content that you have in any point in space, normalized by the adiabatic liquid water content. So this is where the model and the equations are coming from. This you can measure with airplane going through the cloud, but that you have to estimate. You have to have a model for it. And there are a few different models, and we've checked, and one of the papers was to actually first understand what's the best way to calculate these adiabatic water. What is most comparable to the tracer. And once we find out this is the adiabatic fraction, this is the tracer, you can see they do have a lot of similarity. They also have a lot of places where they don't agree. And we now can understand also these regions. So for example, you can see that on the edges of the clouds for the adiabatic fraction, the numbers are much lower. And I forgot to mention, 1 means undiluted, 0 means completely diluted. And here you can see that you have much more dark regions, so much more dilution supposedly, but this is actually not dilution because the tracer is being only diluted by flow, while the adiabatic fraction is being diluted, but you also have evaporation, microphysical processes. So this is why you see on the edges where you have strong evaporation, you have more liquid water content loss due to evaporation, and not to dilutions by mixing. But you can see that the core behaves very nicely. So indeed now we have a way that for the highest numbers, for the undiluted parts, we can estimate those pretty good. Another interesting thing is to see that we have this triangle kind of a shape, which is kind of what you expect from a plume model, but then at the end of it, the core is being eroded and breaks down into those small pieces. And with those simulations, we can actually prove that an airplane that usually goes, mostly in situ measurement, goes through the top of the cloud. And for those kinds of measurement, it's very hard to get those small thermals or small regions of undiluted core. So if we don't measure them, it doesn't mean they're not there. It just means that we have only one pencil going through the cloud and needs to measure something that's pretty small.
If I understand correctly, the microphysics should enhance the dilution.
Yep.
Right? So you would expect more yellow on the right. I don't see it. And
No,
that's
so
blue.
yellow is not diluted and 0 is diluted. So it's those regions. This is, if you compare that point to that point, this is where you see the evaporation happening.
So 0 is more diluted?
Yeah, sorry. Okay? So 0 means basically that you don't have any liquid water content anymore. So we found that, at least in those R-few simulations, we do have undiluted volumes. And of course, it doesn't mean that every weak cloud that we see here in Israel in the summer means that it has an undiluted core. But for pretty developed convective clouds, we do have this core, and they reach almost all the way to the top, only in small areas and small bubbles.
And this picture will change momentarily, right? If you wait like 5 minutes, it's going to...
Exactly. So obviously, it's pulses, it's bubbly, it keeps on bubbling. And I can go back later on if you have any more questions to that video from before. But this is basically the picture. In a snapshot, you have the core of the cloud and you have these core filaments that goes up. Those undiluted core filaments will have the highest buoyancy and highest updrafts. Okay? So that's one interesting point, that those will actually be what we usually refer to in convection as the thermals, where you have these bubbles of air that goes up in the air, up towards the end of the cloud. So, okay, so we have the core, but then the question, how do you get all the rest? I mean, the core is a small fraction of the cloud, so most of the cloud is diluted. So how do clouds mix? So start looking at some average values of all kinds of different cloud variables. So here it's the liquid water mixing ratio, and here it's the relative humidity. We've noticed that if you take a certain level and you average all kinds of variables, many of those variables will have a strong gradients near the edges of the clouds in an order of a few tens of meters. Okay, about 20 to 40 meters, you have strong gradients. And those gradients suggest that the diffusion here, that this is actually where you have diffusion, because diffusion between the clouds and the environment, because this is where you have the gradients. Over here, it's either that you have very strong internal turbulence, that everything, the internal part of the cloud is well mixed, or that it doesn't mix, it doesn't really feel what's going on far in the environment, but you have these gradients, nevertheless. And this is what we call the transition zone, and this is the first idea why we had to go down to 10 meters, because we kind of had a feeling that this transition zone will be on the order of tens of meters. And this diffusion is usually how we think of turbulent diffusion. Usually how in most models think of how clouds mix, usually it's by turbulent diffusion. Like I've shown you before from that paper, where we assume that you have on the lateral side of the clouds, you have these small eddies that act to do turbulent diffusion. To make turbulent, and because you have the gradient, you can model it by diffusion. And interestingly, so we could calculate, because we have the 3D information of the flow, we could also calculate the diffusion coefficient and estimate the diffusion length scale, which comes up pretty close to what we found and we call the transition zone. And this also agrees with in situ measurements with two.
How do you know tau?
We just estimated as the time it takes a parser to go through the clouds or the life
From the adiabatic process?
Yeah. So it's like the average updraft and how much time it takes. Yeah.
It's turbulent diffusion and
because
convection.
so we think of it as you have a parcel going up the cloud and keep being mixed around until it reaches the top. So how deep will it go? So of course, it's just to get the scale of the problem, and this is in agreement with in situ measurements that have observed this transition zone. You need very high resolution measurements, so it's quite hard to get, but who gain very similar numbers for these kind of strong gradients, and with a toy model of Mark Pinsky and Alex from a few years before, which also assumed just diffusion. It's a very basic model of diffusion and evaporation. So now we understand that we also have these small eddies that cause this turbulent diffusion between the cloud and the environment, and which form this transition zone. But again, this transition zone, which is how we usually think of mixing and how a lot of the models are based on thinking of mixing, only captures is not a very large area of the cloud. So you see that this diffusion, turbulent diffusion, can only explain the edges of the cloud.
In previous figures, we showed that like 20, 30 meter diffusion zone. Is that like a single snapshot of like you know, you index the cloud every time step, and then you know you search for where the tension is at each time step, and then you composite based on that. Based on the other thing, it seems like it's much wider though. Like the first part of the block.
Sorry, it seems like what?
It's really narrow. So, whereas previously it seemed like it was much wider though. I was wondering if that's like a snapshot from a single time step, or is that a...
You mean these gradients, the gradients over here, you mean?
Yeah.
Yeah, this is for a snapshot. Yeah,
Okay.
that's a snapshot in the mature stage. Yeah.
Okay, so one snapshot would be like that, but then if you look over time,
So it's pretty stable.
It'll go. Like in other words, there's something that
I see what again. Yeah, so this is a shallow cloud, so its lifetime it's only 15 minutes.
Okay.
So yeah, so for deeper clouds, I mean the scales and everything will probably be scaled up, or maybe even behaving a bit different for thicker clouds. So we have the transition zone, as I said, but then the question remains is what was all the rest? What process can form all these places, all these regions? And for that, I turn to try and see if I can explain it with the toroidal or the ring vortex, which is a much larger scale. So when we have a flow, a strong pulse of flow or a jet flow, usually we'll have this shear all around the flow. So we have the center of the flow, we have a lot of flow. And as you go to the edge of the flow will get weaker and weaker, right? Because of the friction with the motionless air around it. So you have what we call a ring vortex, and you probably know it from looking at smoking a cigarette or just looking at these kind of dolphins and stuff, which also notice it and they like to play with it. So you just give a strong puff, and you will have this vortex that goes all around, symmetrically around the flow, and kind of protect the internal part of the flow as well. And actually I've seen, and I had this intuition because I've seen that, I kind of saw it in my eyes looking at videos of these simulations where you have this strong updraft over here, and here the flow is kind of an average, I will explain in a minute. But you have this strong flow in the middle, which means that in the edges you have the motionless air, so we should get this toroidal vortex, right, as the updraft flow, and indeed you can see, if you can see the arrows here of the flow, that we get this kind of toroidal vortex or ring vortex around the flow.
I think the rings should be on a horizontal plane.
Yeah.
Now you have the jet going this way. Your jet is the updraft.
So you have stuff going all around.
But is it in the vertical plane or the horizontal plane?
The winds. So
the vortex.
The vortex is the vector will point on the horizontal plane, but the flow will be. So if this is Z, so the flow will be on the X and Y. On the Z and X plane. Of course also on the Y plane behind. Like here. Okay, so you have the flow, so there will be like a kind of a flow all around. So this is how it will go. You go with the flow, and the curl will go in that direction. So yeah, in our case where it goes up, the curl will always be, the vector of the curl will be pointing on the horizon of both X and Y. So this is just to show how this is the envelope of a cloud, and here you can see the real wind field of the cloud. So here I noticed that in one side of it you can really see the toroidal vortex, but then in the other side it's all a mess. You can't really see it. So how did I make you be able to see it just a minute ago? And that's because I did some kind of a filtering, so a low-pass filter to filter out the turbulent flow, and then voila, it appears also on the other side of the cloud. So you see that it's not a very coherent ring vortex, but actually you need to do some averaging and filtering in order to really get this kind of a vortex, but it does exist. So in this side it's coherent, so it's also not symmetric. Now, it's not one vortex going around the cloud. In this part you have kind of an eddy that is behaving like that. On the other part, you don't have it. And this is the vorticity field, just to show the point that you have this dipole of vorticity due to the ring vortex, but only after you average and you filter out the turbulence. And this is another cloud, which is a little bit more realistic. It's a bit wider. It's just another realization of a cloud. But here we have a few different pulses and thermals going through the cloud. So it lived for longer, and it was also a little bit wider. But still, you can see that you have this current of the cloud coming out of the cloud, and the ring vortices around it. And here you can see you have another current that is starting to ascend. So now, how can we quantify it and understand what's the role of the vortex on mixing? So first, we do a lateral mass flux assumption. So we can basically assume what is the edges of the cloud. In a way, this is a very rough thing to do, but here we only aim to get a picture of the trend, not to have a very most accurate mass balance of the cloud, because both the border of the cloud is a hard thing to define. But we can find a polygon around the cloud and then see the fluxes on that polygon, around that polygon. So some of the air will go in, denoted here in the red. This will be entrainment of environmental air into the cloud. Blue will be detrainment, where environmental air goes out of the cloud. And now we can integrate all that and get the lateral mass flux. And this is how the profile's first snapshot looks like. So this is two cross sections of the flow. And here, now what you see in yellow, I'm sorry if it's a bit confusing, but I just wanted to emphasize that you'll be able to see the air that is being entrained into the cloud. So this is actually another placer that is being released outside of the cloud. So now yellow will mean highly diluted, blue will be the core of the cloud. And you can see that you have, this is the toroidal vortex I've shown you before, the coherent part of it. So you can see that indeed you have this part over here, and you can see how it pushes air deeply into the cloud, much deeper than the small vortices that occur on the edges of the cloud. Also the other way, so you don't really see it, right? You need it to average and filter out the noise in order to understand. But if you just look at the tracer, you can really see that you have a lot of air coming in of the cloud. And this is actually shown here. This is the profile for the lateral mass flux. And this is, what you see here, this is the maximal updraft. So using ring vortices theory, the maximal updraft will be in the center of that thermal, of that thing that is rising through the atmosphere and is causing the toroidal vortex. So this would be a way to estimate the center of the toroidal vortex, or of that thing. And you see that just below it you have entrainment, as you expect from a toroidal vortex, and just above it you will have the detrainment and the outflow. And this is just to show that this is another angle, another cross-section of the cloud at the same time, just to show that it happens from other sides as well. So the toroidal vortex seems to dominate the horizontal fluxes on the cloud boundaries that you can see from here. You can read the signal is there. And now we can look, once you have this profile, we can actually look at the Hove molar. So this is those profiles, but only how they change with time. Okay, so this is the maximal updraft, and this is how the air or the thermal is rising up through the clouds, where you can see the x-axis is the time. You can see that the thermal is going up the cloud, and below it always you will have strong entrainment, and just above it you will have the detrainment there of the vortex. And it happens until it reaches, it goes through the inversion, and it dies out, and loses its buoyancy. And another way to look at it is to look, okay, so what's happening to the core of the cloud? Because we are really interested in how does this toroidal vortex can really entrain dry environmental air deep into the cloud, because we've seen that the turbulent mixing cannot explain it. So this is the core fraction of the core area, of the cloud. Here in yellow, so yellow means it's the core of the cloud, where the core is most parts of the cloud. And the red polygon here is that polygon around those entrainment regions, and indeed you can see that you can overlap. The maximum speed is obviously in the core of the cloud, where we have the maximum buoyancy. And just below it you have entrainment, which erodes the core of the cloud. So this is all kind of comes together to show that the toroidal vortex is the scale that can actually explain how you entrain air deep into the clouds in order to erode the core and kill the cloud. So it's kind of a La Chatelier principle, where you have the core, you have the largest buoyancy, so air will move up faster, but then if it moves faster, the curl and the toroidal vortex will be stronger, and air will be more entrained. And this is another realization of the cloud, where we see that the cloud lives for longer and is made of a couple of thermals, you can actually still track it. Even the simplified 1D kind of a model of the toroidal vortex can even be captured in a much more complex cloud where you have, supposedly you have a few thermals going through the cloud, but you can still see this positive behavior. You have one dominant bubble or thermal going through the cloud and trains, and then it dies, and then another one comes through the cloud base, another pulse is coming, and it will kill itself until it reaches the highest point. So eventually, the cloud reaches the same layer, the same height, sorry, but just in few pulses until it could actually, but eventually it will kind of be similar in many variables to the other cloud that only had one pulse. But we can see that this way can generalize to a more complicated cloud. And the pulsating behavior is also a question that was a few cloud dynamicists have been interested in. So last, we wanted to understand what's the origin of the air.
Just before you move on to a slightly different subject. So in your picture, what you have is like the step number one is the core that goes upward adiabatically, say, and then you have the formation of these toroidal vortices, and on top of that you have this small-scale turbulence. This is like the steps of
yeah, exactly.
cloud formation and then destruction, or something like that.
Yeah, and the interaction between those scales, I think, will be the most complicated. I mean,
but
yeah.
up to the formation of the ring vortex, you don't really have turbulence.
So you do have, this is where the small scale acts. Yeah, but yeah, so this is where I could go back to it later. But yeah, so in the beginning you can see that the core is wide, and especially in the beginning of the cloud lifetime, the core is still wide. And once the toroidal vortex start to generate, this is when you really start to dilute the cloud. That's the basic idea. You could actually also see it here, in a way. Because this is where entrainment begins to be significant, and then you see that the core starts to be eroded. So last, we also used Lagrangian tracers, which is also thinking of a tracer that goes through the flow, but now in a Lagrangian way. So we just disperse about 1 million particles around the cloud and in the domain, and we follow them using the wind velocity.
What do you mean Lagrangian and then particle? You mean non-interacting?
Yeah, it's offline. This is already offline calculation, just following the flow.
You said Lagrangian, you mean non-interacting particles. They're unaffected by the
So when I say passive tracer, I mean that they are not interacting, they don't have any effect on the flow. So that's both tracers, both the Eulerian one that I've shown until now, and the Lagrangian, they both don't interact with the flow. They are just markers of the flow.
Okay.
You know, it's like coloring a few of the molecules or their parcels and just following them. But now, so these Lagrangian particles, so you can actually follow the flow, and you can also record the thermodynamics variables and all kinds of, and the cloud variables and all kinds of other stuff as they go in time and move in time. So this is one example. So we released this is one particle which was released in the center of the domain in the cloud base, and you can see how it goes up with the flow until it's being ejected and even starting to descend. So I guess this one hits the toroidal vortex, and now it's being detrained and starting coming back down. And the question was actually what I was after is to see if we can see circulation of air. Those particles or parcels that go through the clouds through the toroidal vortex will eventually be trained back into the cloud, because that could have effects on the microphysics as well. So in order to define, to understand the toroidal vortex and to take only those particles that participate in the flow of the toroidal vortex, what I did is taking that Hopf model from before of the entrainment zone, of the entrainment and entrainment profiles, and then I can get, so I can see all this entrainment zone that is just below the maximal updraft, and all these particles that enter in that time and space. So this is the entrainment layer, for example. So in that time, all the tracers, the Lagrangian tracers that came into the clouds on that time and space, I consider them to be entrained by the toroidal vortex. Actually, not all of them, because we also have the small-scale turbulence that Nathan was talking about. So that I could filter, I did some kind of a back-of-the-envelope calculation to the time scales and spatial scales of the toroidal vortex, And everything that is smaller than that scales, I also throw away those tracers because these are ones that have just been in and out the clouds on that layer at that same time and space, but just small vortices that just are superimposed on the vortex. And this is the entrained Lagrangian. This is the histogram of the particles that were entrained by the toroidal vortex. And now I can see what's the origin of those particles. Where did they come from? Did they come from the cloud top or did they come from the environment? So that's the delta Z. So this is, did they go down or up? So first of all, for the toroidal vortex, they must have gone down. This is all they had. They came from the cloud top and went down, right? So they had to go down. But then also, they had to be cloudy. They had to leave the cloud. So all the blue histogram here is those that left the cloud and then be entrained back into the cloud. So you can see that this doesn't explain a lot. There is barely recirculation. And what's more striking is that 90%, more than 90% of the particles are actually coming from the environment. So it's not this coherent vortex. This toroidal vortex is not as coherent as we thought of. And we kind of knew it because we had to do some filtering in order to understand it. But still it gives us, so on an average way, there is a toroidal vortex. But then most of the air coming into the cloud is actually coming from the environment, from the dry environment, and it's not being recycled and humid.
So if you add to it the turbulence, the small scale turbulence, it would be even larger.
Yeah, definitely. You mean the circulation will be larger? Or
The amount of drops that come from within the cloud and then recirculate, the recirculation.
Yeah, the recirculation will be larger. Of course. So 90% of the entrained air is environmental, only 4% is being recycled by the vortex. So that's the final picture, just to add up and summarize the final picture of how now I look at the clouds and the Cumulus clouds, is basically having the core with all the adiabatic processes that can be easier predicted, also for the thermodynamic and microphysical variables. We have the turbulent flow, which is a kind of a diffusion between, if we know what's going on here and we know the profile of the environment, we can kind of understand what's going on here. And then we have the toroidal vortex, this which is, in a way, it's simpler because it's coherent, so it kind of, coherent flow is easier than turbulent flow. But then we see that it's a little bit more complex than what the first image I had in mind, where it's just this coherent flow that recirculates air. So there is I guess there is interactions of the different scales, which add some complication to the problem. But all in all, still, the toroidal vortex, on an average way, can still explain a lot of the behavior of the cloud's dynamics. So to sum up, the adiabatic fraction was compared to the passive tracers, and we've seen that actually we found what's the best way to estimate the adiabatic fraction. High resolution spatial distribution of the adiabatic fraction and the tracer show that we have these small undiluted volumes that exist in all latitudes of the cloud, altitudes of the cloud, and even near the cloud top. But they will be small, so it will be very hard to measure them with an airplane going through the cloud. We also noted about the transition zone, which was before that was mostly recorded by a few in situ measurements and a toy model. And now it's a more complicated model that is able to tell us this story. And we found that the toroidal vortex has a significant role in the cloud's mixing and can explain large-scale mixing and dilution of volumes away from the cloud edge. And this deep entrainment can actually, in a way, maybe explain the pulsating behavior, which has also been a question for the dynamics of cloud filters. Yeah. And that's it. So what's next? It's still, this is a very theoretical, as Nathan noted before, this is a single cloud, it's very theoretical. Now it's interesting to see how much can we find this stuff in nature. It will be hard to measure it. We are trying to think of also of ways how we can measure it. But if I'll just give you this is when I was working with my son in Tel Aviv a year ago, and you can see there's pretty well developed Cumulus cloud, and I think that, this is, it's not nothing quantitative, it's very qualitative, but you can see that the structures look a lot like my cloud, and I think that you can see these remnants of this mushroom shape, which suggests that you have this toroidal vortex in the top of the cloud. And the fact that mixing and dilution is dominated by this kind of a more deterministic flow is, I think, is encouraging, because maybe we can use that in order to come up with ways to have better parameterizations or new models for clouds, for weather and climate models. Because these clouds have been causing a lot of headache to weather and climate modelers and prediction for more than a decade now. So while improving the new parameterizations, that again, as Nathan already noted, this is an old parameterization that is keep being improved, but the community kind of took one direction. And actually, if you go to the 50s, there was a lot of debates if a cloud is a bubble or a plume. And a few people, I guess, just decided that it's a plume. That was easier, came up with simpler models. It showed, I guess, initial results much faster. So everyone went with the plume model and the added diffusivity and all of these kinds of models. And the bubbles models were kind of neglected. So the question is, should we maybe try and develop new ways or old ways and use the bubble model in order to see if we can get any farther with those? And that's it. Thank you all for listening, and I'll be happy to take any questions. Okay.
If I recall correctly, the emphasis on entrainment, understanding entrainment, was largely due to the struggle to get a broad drop size distribution. Does what you've learned here speak to that or not?
Yeah, in one other work it does. The study about the transition zone will actually show also that, that mixing gives you a broader distribution, because you have many different size distribution coming from different parts of the cloud. So the lower the diabatic fraction is, or the tracer, the more diluted it is, the cloud, so it means it's experiencing more turbulent, and so the distribution gets wider. So that it speaks to it, but that problem was actually solved. I didn't solve the problem. It was, there were a few other researchers before that were already aware of that. But it goes back to also another interesting questions of where rain forms, where usually most people today think that it forms in the core of the cloud, where it doesn't get dilute, so the droplets can get bigger or the biggest, and this is where you can get the rain embryos, the first big droplets that can fall and start to collide and have this snowball kind of a process. But then we show that you can also actually get large particles, and again, it's not. The model shows it, but also some other people have shown it before from theory and measurements, that with the mixing you can actually also, unique kind of mixing processes can actually also form that, because of that mixing of many size distribution in collision coefficients. So so it's all related.
In the lateral mass flux graph, I saw that the entrainment is much stronger than the entrainment.
The determinant.
Yeah. Like in the graph, I don't remember the name of it, but the histogram one. This one, the right one. Physics. I was quite confused. Does it mean that more? This seems that more entrainment is stronger than the.
So I'm sorry. It's a bad choice of colors. It shouldn't have been. So here, this is if all these particles were entrained, were captured while they were entrained into the cloud. Yeah, that's sorry for that. It's a bad choice of colors. So all of these particles were particles that came into the cloud, entrained into the cloud, in that time and space of the entrainment layer of this 1D very simple way of thinking of the toroidal vortex. But then the question is, did they come from the environment, or did they come out of the cloud and came back in? Okay, so is their initial point was in the cloud before they were entrained, or if
Technical question. Why did you get this asymmetry between vortices and their signal to noise ratio? We needed to apply just on one vortices the low pass filter.
Oh, okay. So the filtering, let me see. I think I have a slide for it. So the filtering was conducted to all of the cloud. It's just that in some part it seemed to be coherent, in that snapshot, some